And okay, and now let's pass to activity B, which is focused on the development of solar fuels production processes, particularly hydrogen through solar source. And here in this slide, we can see that regarding the solar fuel production, we have two main approaches to the use of solar energy in the for the production of hydrogen. On one side, we can adapt conventional production processes based on the transformation of carbon sources to hydrogen, and possibly using renewable carbon sources such as biogas or bioethanol, and assisted by solar energy to power, obviously, the endothermic reactions of reforming or cracking or gasification. And on the other side, we can produce hydrogen from water as feedstock using solar energy in order to obtain a totally carbon-free fuel that is free from carbon dioxide emissions, both during production and use. And we have been working on both strategies. On one side, carrying out research activities focused on solar reforming of bioresources, and on the other side, studying and developing solar thermochemical and solar thermoelectrochemical water splitting. Obviously, solar reforming of biofuels is a more mature technology if compared to water splitting by thermochemical and thermoelectrochemical processes. So with regard to the development of processes for the production of solar fuels, the division has been operating in this field since the early 2000s. And in this slide, you can see some past projects with the research on reactive materials and plant components like reactors, separators, receiver, and also with design, process simulation, and techno-economic analysis. And so they were referring to the two approaches that I've just mentioned in the previous slide. To the first approach belongs the European Committee projects, which is coordinated by ENEA, which was aimed at developing a compact and innovative reforming reactor to convert carbon fuels, for example, methane and biogas, into pure hydrogen through steam reforming, but at low temperature, let's say about 450, 550 degrees C, assisted by solar energy. And in the project, materials like catalysts and components like membrane reactor were developed to reduce the operating temperature from 800 degrees C, 850 degrees C, which is the conventional temperature for reforming of methane, to about 550 degrees C. And the pilot plant was built connected to a molten salt circuit, which powered the endothermic reaction. And regarding the second approach, we can, based on water splitting, we can cite the SO2H2 project, which now is being followed by a new project, the ISARIT project, which is just ongoing, aimed at developing sustainable thermoelectrochemical processes based on a modification of the sulfur-iodine thermochemical cycle powered by solar energy and electricity. The aim of the project was to develop new materials, particularly catalysts, components like reactors and separators, and also to define the optimal process configuration to reduce, obviously, the cost of hydrogen. Regarding the current projects funded both by national and European research programs, we are still working following the two approaches that I have mentioned. And so on one side, we've been working on the thermochemical hydrogen production from renewable carbonaceous feedstocks. And on the other end, we have been working on the development of thermochemical water splitting for hydrogen production. The most part of the current projects should be completed within the first half of 2025. And here you can see, as an example of the current projects, here I'm referring to the National Hydrogen Project funded by the European Commission. And on one side, we have the hydrogen production through water splitting cycle powered by concentrated solar power technology, aimed at developing new perovskites and new materials to reduce the operating temperature below 1000 degrees C to facilitate the integration with CSP. Here we have been working on thermochemical cycles based on redox reactions, and to perform water splitting. But we have been working on perovskites that can, in order to reduce the operating temperature. And we have also been working on, for example, membrane development for hydrogen separation at high temperatures, in order to develop innovative solutions to increase the versatility and the robustness of membranes on metal supports that have to be used for hydrogen separation and purification processes, and also to be used into membrane reactors. So these membranes are meant to be integrated directly into the high temperature reactors. Okay, and now let's now consider activity C, which is focused on the development and qualification of CST technology for the provision of solar heat for industrial processes. And I would like to evidence that the use of solar heat to supply thermal energy to the industrial endothermic processes has a very wide application potential. Considering that 32% of the total energy consumed globally has to be referred to the industry, and that about the 35% of this quota is destined to endothermic processes at high temperature, let's say over 400 degrees C, and mainly in the chemical industry. Obviously, the strategies for integrating the solar source with industrial processes can be different and strictly depends on the thermal levels of the specific application. And so the main challenge to be faced regards the heterogeneity of the market, target of the market of the solar heat, since the market has different process temperatures and modes of operation. And so the main issue here is the development of standard technologies that can be easily repeatable and easily integrable into the process. And also we need the identification of specific integration strategies in order to ensure operational stability of the process, of the industrial process, and to reduce also the operating cost. And with the aim of, let's say, identifying the main technical aspects related to the integration between industrial processes and CST plants, we have realized at the ENEA Research Center an experimental infrastructure mainly consisting of Fresnel collectors, which will be used for the study of different technical solutions. And furthermore, the experimental infrastructure is aimed at also defining and optimizing the management of the solar field. And regarding the use of solar energy for the production of industrial heat, the division is participating in different projects and European and national projects. And now let's pass to the last point. So the research and development of technologies, methodologies, and devices for application in the smart grid sector and energy grids and microgrids. Particularly, we have been working on the estimation of solar radiation, which is a fundamental activity for the correct sizing of plants to be integrated into the grid and microgrids. And I would skip to the other slide just since I think that time is running. And another research activity is aimed at the forecasting of the global and normal irradiance to predict the energy production and to manage the thermal storage, another very important activity. And now let's consider the activities carried out in the field of thermal energy storage to increase renewable energy dispatchability and to provide ancillary network services. Particularly, we've been carrying out research and development on components and advanced thermal storage system using sensible heat, as already mentioned, and in the configuration of double tank or single thermocline tank. And we have been working on components and advanced thermal storage system using exchange materials. And finally, we've been working on thermochemical storage, as already mentioned. And so let's have a very quick overview on the sensible heat based storages. The molten salt storage configuration investigated by ENEA are different, as I already mentioned. So we have developed a system with two tanks. We have the hot and cold tank, typically sized for, let's say, 8-10 hours of daily storage, which guarantees, obviously, stability of the thermal levels in the discharging phase. And but we have also been working on thermocline tank system, where the tanks, thanks to the compact thermal certification of the salt, we have in one single tank two distinct zones. We have the hot and cold zones, which are separated by this very compact thermal certification. So we can see that this configuration is similar to a two-tank configuration, but here the main advantage is the reduction of the plant investment cost, since the second tank can be eliminated. And this second option, so the thermocline tank configuration, is the subject of research and development in several European projects where ENEA participates, like METSOPS or C+ and RESLAG, most of which are coordinated by ENEA itself. In particular, in the MATS and DOPS projects, we have developed a molten salt storage system with a steam generator integrated, immersed in the tank. And we have built and tested this component in our Casaccio Research Center. Then in the RESLAG project, a pilot storage system was built again at our research center, ENEA Casaccio Research Center. And in this system, the tank is filled with a granular bed of blast furnace slag, let's say industrial waste, in direct contact with the molten salts, which comes from obviously the solar field, in the charging phase, or from the power block, obviously in the discharging phase. Here, the objective is to reduce the cost of the storage system by reducing the amount of salts used for the thermal storage. And at the same time, we enhance the use of industrial wastes. And so in a circular economy perspective. While in the last project here showed in the EOC Plus project, we have a molten salt system with fluid, which confined fluid. So the molten salt is confined into the vessel, does not circulate into the plant. And so we designed this molten salt system and tested it. And the system has two integrated heat exchanger for transferring the heat in the charging and discharging phases. So again, in this system, the molten salt is only the storage medium, and while the heat transfer fluid is diathermic oil. And sorry, it seems it does not work. It's not working. Just a moment. Okay. Okay. In addition to the salt storage system, other sensible heat storage solutions are being developed, such as the storage based on cement. Currently, we have been working on a patent, and cement which operates up to 400 degrees C. And this cement uses low-cost raw materials, obviously, which is readily available and also durable. And in particular, we have developed an innovative concrete mix using recycled materials to reduce the production costs, such as metal wastes from mechanical workshops. We also, within several funded projects, we developed a dedicated test facility at the Casaccia Research Center. And additionally, we have also been working on concrete with phase change material included, stabilized in shape through diatomites, with a concentration up to 5% by weight, to increase the energy storage density and also the temperature stability in the discharging phase. And the use of the thermal storage systems with phase change material, which can be integrated with more traditional sensible heat system, obviously has the objective, the aim to increase the overall storage density. But the main challenge to be faced is the limited heat transport in the phase change material, particularly in the solid phase, when it is in the solid phase. And therefore, two strategy we have has been conceived. On one side, to enhance the exchange surface area between the heat transfer fluid and the phase change material, as visible in the pictures on the left-hand side of the slide. And on the other side, to increase the intrinsic thermal conducibility and diffusivity of phase change materials by the inclusion of nanostructured materials. And so we have worked on different materials, mainly mixtures of binary molten salts as such, and with the inclusion of silica, metals, carbon nanotubes, also to increase the energy storage density and the temperature stability in the discharging phase. And To conclude this survey, I would like to just to briefly mention our work on thermochemical storage. And thermochemical storage is particularly promising because in addition to a high storage density, which is theoretically up to 10 times higher than the sensible heat, the thermochemical storage is virtually suitable for thermal storage on a seasonal scale. Let's say allowing the storage of excess solar radiation when it is available. The thermochemical systems indeed are based on reactive materials which are subject to cyclical and reversible reactions, but they are activated only under certain conditions of pressure and temperature, and therefore they can be this reversible material can store heat in the form of chemical energy for very long periods. The objective of our activity is the development of thermochemical systems which are suitable for obviously the integration with concentrated solar systems, and particularly the attention is focused on two material categories. We have been working on mixed oxides and calcium carbonate supported on mayenite. This last material has been developed in the past in the context of CO2 capture techniques, and that proved to be stable at thermal cycling. And so far, different activities have been carried out, funded by National Research Program, Ricerca di Sistema Elettrico, from 2019 to up to now. And so we have synthesized and tested to thermogravimetric tests the materials, both in powder and pelletized powder. We have developed kinetic models for the dynamic simulation of the charging and discharging steps. And we've been working on the development of experimental equipments, both fixed bed and fluidized bed reactors, and for kinetic characterization of pellets at different pressures. The next step will be the development of real-scale reactor models to take into account both the reaction kinetics and the heat transport within the fixed or the fluidized bed, to provide a predictive evaluation of the effective energy storage density that can be achieved through these solutions in order to open, the way to a scale up of this technology. And okay, so I would conclude this synthetic overview of our research and development activities. First of all, thanking all of you for your attention. And I don't know if there is room for questions. I am more than willing to answer and provide you additional information. Otherwise, obviously, you can ask for more details directly contacting me by email.
Michela, thank you very much for this nice talk, and I'm really sure that everybody has enjoyed. I would like to know if there are questions. Please, if there is a question, let me know.
Okay.
Questions? I can't see anybody raising hand. So let me start with my own question. There's a comment. Can you see the comment, Michela?
Yeah. I see a comment
maybe he has
from
the
the mechanical point of view. Yeah. Have any measures been taken to deal with thermal stress in this equipment? because as we know, high temperature gradients cause thermal stresses, eventually leading to thermal fracture or delamination. I mean, obviously, from the main problems that have been encountered during the testing of components for the CST technology, the main problems have been encountered with thermal storage, the tanks, since particularly the tanks with pebble bed inside and molten salt flowing through this pebble bed to indirectly transfer heat to the pebble bed, as I have already mentioned during the presentation. And in this case, we have we have encountered problems with thermal stresses, and for sure, this is one of the main concern. Anyway, our technology. So the main problems are we have encountered with tanks, since we have been mainly working on linear collectors covered with thermal storage. So we have not been working on, for example, punctual receiver directly irradiated, and this typically one or central towers with central receivers. Typically in the dish technology and in the central receiver technology, the concentration factor that is achieved in correspondence of the receiver, of the window of the receiver, is really very high, and the fluctuation of the ENEA can cause irreversible mechanical stresses. For example, to the glass window, if the receiver is a volumetric receiver with the glass window. So in this case, the technology, this kind of technology, have some problems. I have problems in the management of the receivers, and these receivers are often made by they consist in ceramic material, so they are more exposed to fragility and thermal stresses. While for in our technology, we use linear receiver, tubular receiver that are metallic receivers, so they can stand thermal stresses better than ceramic materials. I don't know if it is the explanation was okay, was clear.
Okay, thank you very much. And other questions? Other further questions, please? Okay, let me ask a question myself about the hydrogen production by the central tower. Do you know of any commercial power plant which produces hydrogen from a central tower?
Okay, and for sure in Europe, no, we do not. The technology is not mature enough to be commercialized. A lot of research projects have been funded by European Commission to develop materials and components and test procedures, and metal oxides, redox cycles have been tested, and a series of projects have been funded, but they have not reached the maturity, the technology maturity. And I know that maybe in the United States there are some attempts to commercialize this kind of technology, but I'm not sure it is still really the technology has been really realized and has produced hydrogen. Some claims were done on this, but honestly, I am not aware of really commercial plants